Hello everyone, welcome back to TechOps tutorial. In this video, we are talking about something very important topic about rolling updates and rollbacks. These two features help you update your application safely without bringing your system down, and if anything goes wrong, you can quickly go back to a previous version. Our goal in this session is simple. You will learn how to deploy new changes with zero downtime, how Kubernetes replaces old pods slowly and safely, and how to roll back in just one command if the update is not working. So let's start and see how Kubernetes keeps your application running even during updates. Let me quickly show you what you are going to learn in this session. First, we will talk about rolling updates. This is how Kubernetes updates your application without bringing it down. Instead of deleting all pods at once, it slowly replaces the old pods with a new ones. This is the safest way to update any production workload. Next, we will cover rollbacks. If your new version has issues, maybe a bug, maybe high CPU, or maybe the application just won't start, you can go back to a previous version with one simple command. I will show you how that works. Then we will look at Kubectl rollout. These are the commands that help you check the status of your deployments, pause it, resume it, or undo it. These are very useful in real-world Kubernetes. And finally, we will talk about production safety, things like readiness probes and control update settings. These help you make sure the update happens smoothly and your user don't see any downtime. So by the end of this video, you will know exactly how to update safely and revert easily in Kubernetes. Now let's see about one of the most important features in Kubernetes, rolling updates. A rolling update simply means Kubernetes updates your deployment step by step. It does not delete all the old pods at once. Instead, it creates a new pods slowly, and only when those new pods are ready, the old ones are removed. This is why your applications stay online during the update. There is no sudden drop, no interruption, traffic keeps flowing. As you can see on the diagram, the old pods are on the left. Kubernetes start creating a new pod one by one, and as each new pod becomes healthy and old pods is removed. This continues until every old pod is replaced. This approach gives you three big benefits: zero downtime, your service stay up; gradual rollout, changes happen slowly and safely; controlled risk, if something goes wrong, you can pause or undo the updates at any time. So rolling updates are the default strategy in Kubernetes because they are safe, smooth, and production friendly. Alright, let's move to the update strategy. This slide compares two ways Kubernetes can update your pods, a gradual update and a full reset. As a system admin or a DevOps engineer, you will hit these all the time. On the left, we have the gradual method. This is the rolling update strategy and it's the default in Kubernetes. With this approach, Kubernetes replaces your pod slowly, one step at a time. New pods comes up, old pods goes down, and user barely notice anything. There is no downtime and the rollout is controlled. And it's a great when you want a smooth and safe upgrade. Now on the right side, we have the fast but disruptive option, the recreate strategy. With recreate, Kubernetes kills all the old pods first, everything stops, then it brings up a new version. This means downtime, but it can be useful when you are making changes that won't work with all old version running. It also gives you a complete fresh start. So in short, rolling updates is your safe, no downtime approach. Recreate is your clean slate but downtime heavy option. Pick the one that fits your rollout and your user. Now let's take a look at how rolling updates actually work. Kubernetes gives us two settings that control the speed of the rollout. These are MaxUnavailable and MaxSurge. MaxUnavailable tells Kubernetes how many old pods can be down at the same time during the updates. So if the number is small, the rollout is slow but safer. If it's larger, you move faster but take more risk. MaxSurge is the opposite idea. It tells the Kubernetes how many extra new pods it can create while updating. These are temporary extra pods that helps the application running smoothly while the old pods are being replaced. Together, these two settings control the pace, how many old pods can disappear, and how many new pods can show up earlier. By default, Kubernetes sets this to 25%. It's a nice middle ground that balances safety and speed. Alright, let's talk about revision numbers. This is how Kubernetes keeps track of every changes you make to a deployment. Every time you update your deployment, maybe you change the image or apply a new YAML, Kubernetes create a new version. In the slide, you can see the flow. Revision 1 is the initial rollout, revision 2 was a buggy update, and the revision 3 is the current version. The nice thing is, this whole history is automatically tracked. You don't have to enable anything. Kubernetes keeps a list of all ReplicaSet for you. And because Kubernetes stores this version, you can roll back at any time. If a new release causes issue, you can jump back to a previous stable version instantly. You can check this history using kubectl rollout history deployment / followed by deployment name. This shows each revision and the change that triggered it. So overall, revision numbers makes your deployment safer, easier to review, and quick to recover when something goes wrong. Now let's look at a key kubectl rollout command. These are the basic you will use to control and monitor the deployments during updates. First, we have the status command. Kubectl rollout status deployment / web-app. This is a deployment name. This lets you watch the progress of rolling updates in a real time. It's great when you want to see if everything is moving smoothly. Next is the history command. Kubectl rollout history deployment / web-app. This shows all previous versions so you know exactly which version you might want to roll back to. Then there is a pause command. Kubectl rollout pause deployment / web-app. This temporarily stops the rollout. It's useful if you want to test a canary release or check something before continuing. To keep going, you use the resume command. Kubectl rollout resume deployment / web-app. This picks where the rollout left off and finish the update. And finally, the rollback command. Kubectl rollout undo deployment / web-app -2 revision equals to 2. This takes the deployment back to a previous version. If you don't specify a number, it simply roll back to a last good version. So with these commands, you can fully control the lifecycle of deployments during updates. Alright, now let's take a look at what actually happens during the updates. On the left, we start in the initial state. All three pods are running version 1. Everything is stable. Then Kubernetes begin the rolling update. This is where we see mixed version. One old pod get removed and the new version 2 pod gets created. So for the short time, you have both versions running side by side. This is normal during a rolling updates. And once all the old pods are gone and all new pods are up, we reach the final state. Now all three pods are on version 2 and the update is completed. Down at the bottom, you can see how this looks in the terminal. We are watching the pods in real time and you can see the status change. One pod is terminating and another is being created, and the others are already running. This is why rolling updates feel smooth. Kubernetes handles each step for you, and you can follow everything live with a simple command. Now let's talk about rollbacks. Basically, the undo button for your deployments. In this example, version 2 has a problem. Maybe it's crashing, maybe it has a bug, or maybe something just fell off in production. Instead of trying to fix it live, we can tell Kubernetes to go back to the last stable version. That's what the arrow in the slide shows. Kubernetes rolls us back from version 2 to version 1 with a single command. Down in the terminal, you can see the exact command we use. Kubectl rollout undo deployment /my-app. As soon as we run it, Kubernetes replaces the broken pods with a older and stable version. Rollbacks are huge safety net in production. If a new release goes wrong, you can restore stability right away and then take your time to dig into the root cause. It's fast, it's simple, and it saves you from a lot of stress. Next, let's look at how Kubernetes protects your user when an update goes wrong. This slide shows how Readiness Probes act as a safety checks. Every pod has a small health test, and Kubernetes only sends the traffic to a pod if it passes that test. So if the new version is not ready yet or it's failing its health check, Kubernetes simply keeps traffic away from it. When a pod is marked as not ready, the rollout actually pauses. This stops things from getting worse and gives you time to fix the issue without breaking production. And the best part is, your user never sees any error. The load balancer keeps sending traffic to the old pods that are still stable and healthy. Even if a new update fails, Kubernetes stops it, keeps your old pod running, and makes sure your service does not go down. This is the one main reason rolling updates feel safe to use in real production environment. Alright, let's walk through some best practice that help you keep your deployments reliable and avoid downtime. First, always test in staging. Before deploying a new image in production, always test it in an environment that is similar to the production. This small step helps you to avoid unexpected issue later. Next, use Readiness Probes. Readiness Probes make sure traffic only reaches the pod that are actually ready. If a pod is still starting or not healthy yet, Kubernetes won't send the traffic to it. This helps to prevent those random errors during the rollout. Another thing to look at is tuning your parameters. Adjust values like MaxUnavailable and MaxSurge based on how your application behaves during the startup and how much the rooms you have on your nodes. A small tweaks here can make your rollouts much smoother. Then make sure you monitor your rollouts. Use command like kubectl rollout status and watch your metrics. If you see error rates going up or latency spike, you know something is not right and you can stop the rollout earlier. And finally, keep a history of your revision. A reasonable revision history limit lets you roll back to a stable version anytime you need to. The default is usually enough, but make sure it fits your workflow. These practices together help in keeping your deployments clean, predictable, and safe, especially when you are aiming for zero downtime. Alright, let me quickly walk you through what we are about to do before we start the demo. We start with version 1 running across all pods. Everything is healthy and the application responds normally. Then we begin the rollout to version 2. Kubernetes replaces the pod one by one and you can see the new version slowly taking over as each pod gets updated. But during the update, a failure pops up, a couple of new pod crashes, readiness probe fail, and Kubernetes stops the rollout to avoid breaking production. Since the update is failing, we use a rollback. With one command, Kubernetes restore the previous version and all pod go back to a stable state. That's the full flow. Healthy state, rollout state, failure detected, and rollbacks kicks in. I will show you this live now so you can see exactly how it works in real time. Let me access the terminal. As you can see on my screen, I have started Minikube server. You can see the Minikube server is running, and you can also see the output of kubectl get nodes. I have only one node, and I have already created a YAML file. Let me show you that before deploying. Deployment -v1. This is the YAML file. I will apply it. Kubectl apply -f deployment -v1. Kubectl get pods. Containers are getting created. I have added a replicas of 6. So 6 containers are getting created. One container is running. Let's wait for a few seconds. All containers are running. Let's test the application version like kubectl. I will do port forwarding. Deployment name is web. I will give 8080 or 8081 5678. So let's curl. I will open the terminal, another terminal, curl localhost. We have given 8081. So you can see you receive the output version 1. This is a stable baseline created. V1 is healthy. Now let's see rolling updates to another version. This will be a buggy release. We will demonstrate a failing rollout and how Kubernetes protects live application. Let's see. Update the deployment to an older version, something like 0.2.2 that may not exist locally and could fail to pull. I will run kubectl set image deployment /web hashicorp /http echo : give the tag 0.2.2.2. I have forgot to add a record. So we are updating the deployments to a new version. Kubernetes replaces old pods gradually while keeping the application available. This ensures zero downtime even if the new pod fails. Kubectl get pods. So the old pods terminate slowly, serving traffic until the new pods are ready. New pods fails due to the image pull issue, simulating a broken release. Some old pods remain running, means live traffic is unaffected. So let me show you kubectl rollout status deployment /web. This will show you waiting for the deployment web rollout to finish 3 out of 6 new replicas have been updated. Kubernetes paused the rollout because the new pods are failing. It keeps retrying the pods until the progress deadline is exceeded. This safety mechanism prevents downtime in production by ensuring unhealthy pods don't replace working ones. Here you can see these are the old pods which are running since 4 minutes. These are serving live traffic, and the new pods are getting an image pullback error, means it is failing. Let's inspect pod failures and verify the live traffic. Kubectl get pods, run kubectl logs. All are waiting to start, but they are failing to pull the image. Logs confirms why pods fail: bad image, crash or invalid arguments. Any pod failure blocks the rollout while keeping old pods active. Old pods continue serving the traffic, means live application is safe. To verify, we need to do port forwarding. Kubectl port forward deployment /web 80815678. I am running this command once again. Here you can see we are already running this command with 8081. Let's see what error we receive. Failed to create with the following errors: unable to create a listener because 8081 is already in use. Unable to create a listener. So for this, what we need to do, let me show you the troubleshooting step. As this is for a testing purpose, you run ps aux grep kubectl. Here it will show this 8081 service is still running. You can kill this port forwarding with kill -9 followed by this process ID. Like this you can kill, or the another method is you can use pkill -f. You can run kubectl. This has been killed. By running this command, this process has been killed. Kubectl port -forward. Let me rerun this. Let's recheck once again. ps-aux grep kubectl. Here you can see this is the service. Instead of giving up a process ID, what I will do, I can run this command. Let's see if this works. I killed this process. Yes, this has been terminated. In this both way you can kill the process. Let's go back to our demo. Let's do once again port forwarding, and you can do curl. This is still running. Test with curl localhost We have given the port 8081. You need to receive the version 1.0.1. Here you can see handling the connection for 8081. Kubectl get ports. Here you can see the old pods are still running and the few new pods are getting failed. Despite rolling failures, users still get response from old pods, reinforms the rolling update strategy, ensures high availability even when a new pod fails. You can check kubectl get ReplicaSet. The old ReplicaSet is this, still has all healthy pods running and serves live traffic while the update is in progress. And this is the new ReplicaSet. It has been created 7 minutes ago and the previous one 10 minutes ago it has been created. This is the new ReplicaSet. All pods are failing. Here you can see desired is 3, current is 3, ready is 0. All pods are failing because ImagePullBackOff error shows that the rollout is blocked due to the unhealthy pods. As you can see, we have given a ReplicaSet with 6 pods, but the total pod count increased temporarily. You can see more pods than expected because old pods remains running until the rollout succeeds. This demonstrates Kubernetes safety mechanism in rolling updates, protects the existing traffic while deploying the new version. ReplicaSet tracks the state of old and new pods separately. This is why the Kubernetes can safely roll back, retry, or pause the deployment without affecting live users. Now let's roll back to a last stable version. Before that, let's check the current deployment image. Kubectl get deployment web-o YAML. Let's grab this to an image. Here you can see this is the image. We are checking the deployment spec to see which image the pod are trying to use. This helps us understanding why the new pods are failing with ImagePullBackOff error. Let's check the rollout history. Kubectl rollout history deployment/web. Here you can see I run this command at the beginning of this demo. When you roll back, Kubernetes create a new version with a restore previous configuration. Kubectl rollout undo deployment. Here I am not specifying any version. You will receive the output like deployment.app/web rollout back. This command restores the deployment configuration to the previous stable revision. Kubernetes will try to create a new pod based on the stable revision. Kubectl get pods-w. Failing version 2 pods terminated. Old v1 pods come back. All pods eventually running or a ready state. One started in running. Deployment web successfully rolled out. This is the command where you can check the status of the deployment. Let's see the port forwarding is running. docker localhost 8081. As you can see, let's remove -w. All pods are running and the total count is 6. And also we are verified the version 1. App restore to a stable version by running kubectl. We will run here only kubectl rollout history deployment/web. Now you can see, let me show you first. The revision was none, and the revision 2, this is what we deployed. And when we roll out to the old version, so revision 1 is been hidden. You can see only revision 2, and this is the rollout what we did recently by using undo command. By using this command, when we run this command, we have not used -- record equals to true. That's why it has not been recorded. Kubernetes shows all the revision of your deployment using kubectl rollout history. Deployment/web. Each revision represents a change in the deployment specification. Kubernetes keeps a history of every deployment change as a revision. When we roll back, Kubernetes does not go backward in a number. It actually creates a new revision that contains the old stable configuration. This is why after rollback, we can see a new entry like revision 3, but with the image and specification of the stable v1 deployment. Why this is helpful? You can clearly see which command creates each revision. You can track which version was buggy. Rollbacks always creates a new revision. They don't overwrite old ones. Makes debugging and auditing much easier. If you don't use -- record, the change -cause field will show none, but rollbacks still work. The only difference is you won't know which command creates that version. Here you can see the version 1 is disappear. Let's check the revision history limit. You can check the history revision limit very easily from the deployment YAML. Just run kubectl get deployment web -o YAML grep revision history limit is 10. We can directly grep it. If it's set, you will see something like revision history limit :10. If you don't see anything, that means Kubernetes is using the default value 10. Why revision 1 is disappear even though the revision history limit is equals to 10? Let's understand. Let me run that command once again. Revision 1 did not get deleted. It just not shown by kubectl rollout history command after the rollback because of how Kubernetes rotates the revision number during rollbacks. Here is exactly what happens in this case. Revision 1 is a version 1 deployment and revision 2 is version 2 deployment which was buggy and failing. After rollback using the command, just say kubectl rollout undo deployment/web. rollback creates a new revision instead of reusing the old one. Before rollback, revision 1 is the deployment version 1 and revision 2 is the deployment version 2, means a buggy or failing. After rollback, revision 3 created. It is same deployment as a version 1. This is the new revision created during rollback. And revision 2 means a deployment version 2 which is kept for the history, and revision 1 is hidden. Why revision 1 is hidden? Revision 1 has the same pod template specification as the revision 3, same image, same argument, etc. Kubernetes hides older revisions that are identical to a newer, active revision to avoid redundancy. It is not deleted, it's just not shown in kubectl rollout history. The key point here is rollback creates a new version. Kubernetes does not reuse the old revision number. Only unique pod template specifications are displayed in kubectl rollout history. Older revision with identical specification are hidden, not deleted. Revision 1 is equals to revision 3. That's why revision 1 is hidden. If the specification were different, even an older revision would still appear. So, in summary, rollback always create a new revision. Kubectl rollout history shows only active or unique specification. Identical old revisions are hidden to reduce redundancy. That's why we observed in rollout history command output revision 2 and revision 3. If you want to understand more deeper, let's do a small demo for multiple unique revision. I will update the deployment multiple times with a different image to create a unique pod specification. Example, kubectl set image deployment. I will use the same thing /web. Web equals to hashicorp /http echo 0. Now I will use 0.3.0. This is only for demo to understand how history has been recorded. So again I will update to 0.3.1. One more time, let's update to 0.3.2. Each set image command creates a new unique version and it will show in kubectl rollout history command. Let's run now kubectl rollout history deployment /web. This is the expected output. Each image update create a new version. If your rollback to a revision has the same spec as the older one, the older revision may be hidden in rollout history to avoid duplicates. Only unique pod specifications are visible in the history. Now let's move to the slide. Alright, let's quickly wrap this up. Today you learn how rolling updates help you replace pod gradually without downtime. You also saw how safe rollbacks let you jump back to a stable version when something goes wrong. We covered the key kubectl rollout commands. You also saw why readiness probes matter so much during updates. They protect user by stopping traffic from hitting broken pods. And finally, version history. Kubernetes keep track of revision for you, which make restoring to a good state fast and easy. Thanks a lot for watching this tutorial. If you found it helpful, feel free to like, subscribe and hit the notification bell so you don't miss further content, and see you in the next one.